Okay. All right, why don't we get going here? So the warm-up question has to do with resolution. Remember, resolution is this idea that all imaging systems, including our eyeballs, require a minimum angular separation of objects in order to be able to distinguish one light source from another light source. So you can see here in this problem, you have the somewhat contrived scenario where a person only has one eye open, but it still works. Looking at a car's headlights coming in towards her at night gives you the aperture, the openings of her eyeball, gives you the distance of separation of the two headlights, and it gives you the wavelength of light that's being emitted. Okay, and then asks you to calculate the distance of the car, how far away the car will be when the woman first can basically distinguish the two images from each other. And so if you recall last week, we talked about this. And because it's a round pupil, right, then we're going to use the round aperture Rayleigh criterion, which is the angular separation equals 1.22 times the wavelength divided by B. B would be in the size of the aperture opening. And so what we can do first in this problem is we can use that equation to figure out what is the minimum angular separation required by the eyeball in order to distinguish those two headlamps as being separate. And you can see there you get 1.6 times 10⁻⁴ radians. Then what we're going to do is we're going to create a little sort of image, or I should say drawing again. And just remember that 1.2 meters is kind of that arc length all the way on the right. And the angle of that arc is what we just calculated, 1.6 times 10⁻⁴ radians. And so then we're just going to use the very simple equation that's geometry based that says basically if we want to know the D in this case would be the distance, or you could think of it as the radius of that big circle that we've talked about. Then really it's the definition of an angle, right, in radians is the size of the arc length divided by the radius of the circle. So it's S over D in this case, using the letters that we're using. And the S we know is 1.2. And so then we just solve for capital D. When we do that, we get a value of 7,500 meters, which is 7.5 kilometers. Okay. So there you go. Again, if you have questions or comments, as always, put them in the chat box. I'm going to keep going here, but I can always double back and answer those questions as they appear, or as I see fit during the presentation. Okay, so like I said today, I want to talk about this week's guest speakers, and then I want to show you a few slides, one on a concept called nuclear diffraction, and the other one called thin film interference, and then we'll get to the breakout rooms. So those of you, some of you missed it yesterday, but Robbie Gottesman spoke yesterday for it was about a 30-minute session. Really fun, really fascinating, nice person. It was recorded, and I will be making that available with the other guest speaker lectures here shortly. So just realize if you missed it, you will get a chance to listen, see it later on. And then you do have an opportunity today. Today at 1 o'clock, Spider Woman, Oregon Professor of the Year in 2011. Okay, so strongly encourage you to join in today if at all you can. These are great talks that people are giving, and I'm really enjoying them because just kind of the wealth and breadth of experience and advice they're giving to everyone, including high school students like yourself, I just think is fabulous. Okay, so and then I just want to remind you the due dates. Due tonight is the 3rd progress update on your legacy project. Okay, just want to emphasize if you're a little behind where you thought you were going to be, not a big deal. Just keep plugging along, keep making the progress that you can, and revise your project milestones accordingly. I do want to see the legacy projects turned in, so to speak, by next Thursday. So we're talking a week from today. Okay, so with that in mind, let's start talking about nuclear diffraction. So I want you to recall this slide that I showed you a few sessions ago. And this is really key again, because we want to revisit this idea of diffraction. Remember, diffraction happens when a barrier is placed in the way of a wave or a set of waves, and when the barrier width or the barrier separation is somehow close to the wavelength of the incoming waves. And that's where we get noticeable diffraction. And you notice here, single slit diffraction, we get that pattern that you see over there on the right, where you get that bright maximum in the middle, and then you get the dark fringes, the first minimums, et cetera, et cetera. Well, somewhere along the way, some scientists thought of a really novel way to use this property, diffraction, to measure the radius of nuclei. And so if you think about it, the diameter of a nucleus can be determined by measuring the diffraction if you take a beam of high energy electrons or neutrons. Because remember, those electrons or neutrons, like we've talked about, have a Debroglie wavelength. And their Debroglie wavelength is on the order of magnitude of the diameter of a nucleus. And so what happens in these experiments is that you get the nuclear barrier, meaning the nucleus itself, acts like a single slit having a certain width d, equivalent to its diameter. And so if you look in section 12.2 of your data booklet, there is this little formula that seems completely out of place when it because section 12.2 is all about nuclear equations, nuclear physics. And so this sine theta equals lambda over d appears there. And I just want to make sure you realize this is why it appears there, is because we can use this property of diffraction and the idea that particles, electrons, neutrons, exhibit wave-like properties to measure the radii and the diameter of nuclei. So let's just do a quick sample problem. I'll walk you through it here. So here's the example. If I take a beam of 80.0 mega electron volt neutrons, and they're diffracted upon passing through a thin lead foil. Okay, so I have a thin sheet of lead, meaning these are lead nuclei that I'm trying to basically estimate the diameter. And notice behind the lead on the screen, I see a diffraction pattern, and I can measure that. I can measure the angular separation from the center point of where I aim that beam to the first minimum. And let's say I measure that angle to be 12.6 degrees. Okay, the question is to estimate the diameter of the lead nucleus. So how are we going to approach this? Well, the key ideas here I've outlined in red, by the way. So you can see calculations in black and key ideas in red. So the key ideas here are you're going to use the Debroglie wavelength equation. The wavelength of a beam of neutrons is equal to Planck's constant divided by the momentum. And you're going to use the mass of a neutron as well, as you can see it's given there. And so what we can say is, first of all, with the kinetic energy, what we want to do is convert from the electron volts or mega electron volts to joules. And so you can see that I've just done a quick little conversion using the conversion factor to get a certain amount of kinetic energy in joules. What do I do from there? Well, we know kinetic energy is related to momentum, and I don't know that I've ever formally presented this equation to you, but this equation is sometimes used in circles, but it doesn't matter. Even if you don't know this equation, you know kinetic energy equals, if kinetic energy equals 1/2 mv squared, and we know momentum is mass times velocity. So this basically, the equation you see there is those two combined. So now that we have the kinetic energy in joules, we can then plug through those equations, those pair of equations, or this one equation down here, to get a momentum value. And that momentum value is this one right here, 2.068 times 10⁻19 kilogram meters per second. Once we get the momentum, we can use the Debroglie equation to find the wavelength, okay? And notice that's what I've done here. You take 6.63 times 10⁻34 divided by your momentum that you've calculated, and you get a certain wavelength, 3.207 times 10⁻15 meters, okay? Again, the key idea here is the neutron, or a key thing that makes this work, is that the neutron's Debroglie wavelength is on the order of magnitude of the radius or diameter of the nucleus. Because what you see here is when I then go back to this original equation up here, now I have the wavelength, the Debroglie wavelength, I have the angle that's given me in the problem. I can then go ahead and solve for the diameter, and you can see that the diameter, the estimated diameter based on this experiment for the lead nuclei is about 1.5 times 10⁻14 meters. Again, on the order of magnitude of the Debroglie wavelength of the neutron beam. Pretty awesome, isn't that? Okay, all right, here we go. Let's liven this up with a quick little joke. Now remember, when you hear the punchline, unmute, laugh for 2 seconds heartily, and then remute. You ready? Here we go. What lights up a soccer stadium? What lights up a soccer stadium? Well, a soccer match. Not all of you are unmuting, and that upsets me. So anyway, just remember that next time. Okay. And some of you might take you a few seconds to get the joke, and that's okay. It took me a few seconds to get this joke. Anyway. Okay. So on to the second topic for today, which is thin film interference. And this is really fascinating to me. It can be a little hard to understand, and we're going to need to take a few slides to kind of build up to understanding where it comes from. But please, again, as always, please try and just, more than anything else, listen and understand conceptually what's going on. Don't get too bogged down by trying to copy down everything or by getting bogged down too much with the math. So thin film interference, you've seen this. Oil slicks, gasoline spills on water, soap bubbles, insects and feathers. They can create this really interesting, very colorful sort of, kaleidoscope type thing that you see with your eyes. And those are all examples of what we call thin film interference. So what we're going to walk through here is kind of the science, the physics behind it. Okay, so let's get right into it. We got to start out with something a little simpler, and it's something I would normally do this in class if we had session in class. But you can imagine having a heavy rope on the left there, kind of transitioned at one point in time right here to a lighter rope, thinner rope. Okay. So if I send a single pulse down that heavy rope from left to right, it'll eventually get to that transition point between the heavy and the light rope, and let's see what happens there. All right, let's watch. Okay, notice, I'll just do it one more time. Notice what happens at that transition point. You get a reflection and you get a transmission. Key idea here is both the reflection and the transmission are in phase with each other. In other words, I have a crest coming in, I have a crest going out, reflected back, and I also have a crest transmitted through. Okay? And the reason for this is because the speed in the heavy rope is slower than the speed of the wave in the light rope. Okay, that's another key idea here. Let's flip the scenario around. Let's say I first send the pulse down the light rope, and then it hits a transition point right here again, where the rope is heavier. Okay, what's going to happen this time? Let's observe. Well, it's a little different. And just in case you missed it, there it is again. So notice what happened here is the transmitted wave still is in phase. Crest came in, crest got transmitted through the heavier rope. But the reflected wave pulse is not a crest, it's a trough. So what we say is there's been a phase shift there, okay? So the reflection is out of phase while the transmission is still in phase. Okay, keep that in mind. And notice this is a scenario where we're going from faster medium. The wave is traveling faster in the lighter rope and is traveling slower in the heavier rope. Important to keep that in mind. All right, so I'm kind of summarizing here what I just talked through. If a wave enters a boundary from medium where the wave speed is lower, it will reflect in phase. Okay, so notice that's what it's saying there. Crest comes in, crest goes out from heavy to slow. Excuse me, heavy to lighter, which means slow to fast. I apologize. Slow to fast is the key idea here. If I go slow to fast, there's no phase shift on the reflected wave. The second scenario is if I'm going from fast to slow, and I get a phase shift on the reflected wave. Notice crest coming in, trough going out. The third key point is this, that in all the cases, the wave that is transmitted through the boundary is always in phase. So there's no phase shift for any sort of transmission of wave from one medium to another. Okay, it's all about the reflection. Okay, so those are 3 key points. Now let's see how this plays out. So these are mechanical waves we're talking about here on robes. But as I've said before, oftentimes what is true for mechanical waves is also true for electromagnetic waves like light. And that is the case in this scenario. And so what we have here is, let's say I have a thin film of a certain substance. Could be gasoline, could be a coating that I've put on some sunglasses. And I've made it really thin so that the thickness, that D is pretty small, okay? And that film has some sort of index of refraction that we're going to say is N. Okay, so now that I send light waves upon it, okay, light waves come in, and just so you know, for illustration purposes, this light wave, this purple wave is coming in at an angle, but I want to make sure you realize that in reality, the reason I only I show it at an angle is so that you can kind of see what's going on. But in reality, if I was to draw this light wave is coming in at an angle of 0, okay, like that green arrow that I just drew. Okay, so what's going to happen at that top surface? Because remember, there's air. Air is the one medium, and then this thin film has a different medium, which is with a different index of refraction. A part of it is going to be reflected, and a part of it is going to be transmitted. Okay, and we know that basically the same thing will happen at the lower edge, right, as well, when it goes from the thin film back to air. So, so you can see there's going to be also a series of transmissions and reflections. And the question is, can we figure out what's going to happen at each one? Is there going to be a phase shift or not, based on our previous scenario of the ropes? So let's see what we can figure out. Okay, so if you look here, the speed of the light in air is basically pretty much close to the speed of light in a vacuum. And the speed of light in the medium, though, is going to be significantly slower, right? And we know how much slower it's going to be because, remember this relationship, N equals C over V, so V equals C over N. Index of refraction is what N is. So at the top surface, does the reflection get a phase shift? Well, let's see. We're going from fast to slow. And in the rope scenario, yes, we did get a phase shift because we're going from fast to slow. So notice that the incoming phase is that phi. The outgoing, the reflected phase, is going to be phi plus pi, okay? Pi meaning 180 degrees out of 180 degrees phase shift, okay? What about the transmitted wave? The transmitted wave, remember again, does not get any sort of phase shift, so it just keeps that original phase of phi. Okay, what about at the bottom surface? Does the reflection get a phase shift? Well, it's going from slow to fast. No, so basically the reflected wave does not get a phase shift, okay? So notice that is phi as well. And so then what happens at the, upper surface? We know that whenever there's transmission, right? It doesn't matter whether it's slow to fast, fast or slow, there is no phase shift. So notice that that smaller purple wave there that is to the right of the fatter one, the original one, comes out with the original phase, whereas the reflected wave, right, the one that was reflected at the top surface, has gotten a phase shift. Okay, so that's key. We have two waves now that are out of phase. Now you might say to yourself, yeah, but they're not meeting at the same place in time. Well, that's true, but remember the light is coming in continuously. So I have a subsequent wave that is going to travel down to the bottom there, and it could meet at the same time and place as a reflected wave that's coming in later on. Okay, so remember, these are a series of waves that are coming, not just one wave pulse. So now we see that we have the conditions set up where we can maybe get some sort of interference. Remember, because if things are out of phase, if crest meets trough, remember, we get destructive interference. And so let's see what conditions have to exist for this to work. So the distance the light is traveling inside the film is 2D. And I just want to emphasize this point again. I made it once already, but these are actually coming in straight in, as I'm drawing there with the green arrow, and then maybe a subsequent one with the red arrow, okay? But the only reason we draw them at an angle is because that way you can kind of see better what's going on. So this angle has been greatly exaggerated for the purposes of illustration. So we know the distance down and back is 2 times the thickness of the film. Okay, and the speed of light in the medium is, we know, C over N based on Snell's law and the Snell properties we talked about. And so if we go back to our kinematics understanding, speed is distance over time. Okay, so if that's the case, we can solve for time. Time is distance over speed. We know for the wave that gets transmitted through the film and then reflected from the bottom, that's going to have a distance of 2d, and the speed is going to be c over n. So you can see the time it's going to take for that red wave that I showed there is going to be 2dn over c to get back to that sort of exiting the upper surface. Okay, 2 times the thickness of the film times the index of refraction of the film divided by the speed of light. But outside the medium, remember, wave crests keep coming, and the wave crest will travel m wavelengths in a certain time, right? And they're going to travel those wavelengths, again, using the same simple equation, time is distance over divided by speed. So it's going to travel m lambda wavelengths, that's the distance it's traveling, divided by c, the speed of light. So notice we have 2 equations for time. One for the purple waves that are on the surface there, and the other one for the red ones that basically get transmitted and then reflected from the bottom. And remember, if this time lapsing is the same, if we set these equal to each other, that means the waves are actually meeting at the same place at the same time. And so notice if we set these equal to each other, what do we get? We get the scenario where there is basically a set of conditions where if this is true, if 2dn over c equals m lambda over c, then I have 2 waves meeting that are out of phase with each other, 180 degrees out of phase. We're going to get destructive interference. Crest is going to meet trough, and you're going to get a cancellation of the light, so to speak, cancellation of the wave. So that's what we call thin film destructive interference, when these conditions are just right so that the left side of the equation, twice the thickness times the index of refraction, equals a certain multiple of wavelengths of the incoming light, you're going to get destructive interference. Now, if you recall, the conditions for constructive interference and destructive interference are always offset from each other by half a multiple of the wavelength. So I'm not going to go through it here, but you can deduce that basically if the rejoining rays basically if they're off by half a multiple integers, notice m plus 1/2 down here, then you're going to get constructive interference, meaning crest is going to be crest, trough is going to be trough, and that certain color is going to look brighter. So notice what's happening here. Depending on the wavelength of the light, the thickness of the film, and the index of refraction of the film, certain colors are going to get canceled out because those wavelengths are going to be canceled out, and other colors are going to be brightened because they're going to be constructively interfered with. Okay. Question has come up. What is m in that equation? M is any positive integer, Ian. Okay, so m is 1, 2, 3, 4. It could be any positive integer. Because remember, this is a series of waves coming repeatedly. Okay, so notice we have these 2 conditions here for thin film interference. One is destructive, meaning certain colors are going to be canceled out, not going to appear, and other colors are going to appear brighter. And so this kind of starts to explain, or this does explain what happens like with the soap bubbles. You get a brightness of certain colors, and you get also basically a spreading out of colors as well, because sometimes when they come in at a slight angle, right, then the refraction that happens is going to kind of refract each light slightly differently. So there's a couple things going on here when you look at something that's iridescent and colorful kaleidoscope-wise. But this explains why certain colors are canceled and why you get sort of that very vibrant set of colors. So these are all scenarios. I'm really not going to spend much time on the slide, but these are all scenarios. Because remember, if you think about this, I can have, in this scenario right here, I have fast, slow, fast, okay, which is kind of the scenario we just went through. But I could also have a scenario here where I have fast, medium, even slower, medium. Or I could have slow, fast, slow, okay? And so notice you get certain scenarios that happen, and depending on how many phase shifts happen, you can either get constructive or destructive interference. It can get a little tricky, and you have to really kind of walk through it. And I'm not going to do that today with you, and there's really no need to unless you want to study this more in depth. So you're not going to do an IB test, but I just want to point out for future, in the future, if you ever find yourself confused, there's good reason why you could be confused just by looking at your data booklet. Because if you look over here, subtopic 4.4, okay, this tells you constructive interference, path difference, and lambda. And then over here, subtopic 9.3, this tells you, it seems to tell you something that's the exact opposite, constructive interference, n plus 1/2 lambda. You have to remember that in 9.3, we're talking about specifically about thin film interference, and only the scenario that I just mentioned where you're going fast, slow, fast. Okay? The data booklet doesn't tell you that, and that's kind of a downfall in my opinion. Okay, so this is only true for one particular scenario of thin film interference, whereas this wave behavior is generally true in all cases. Okay, when we're talking about path difference through multiple slits, Young's experiment, et cetera, et cetera. So try and keep that in mind. Okay. And so just a couple of examples here. Thin film interference has some very wonderful uses. You can see in nature, certain animals, insects, for example, sometimes have a thin film on their wings, and that allows them to be quite colorful, as you can see that butterfly there. It also has some practical applications. If you look down there on the left, eyewear manufacturers often will put a thin film on sunglasses or just any glasses to reduce the glare, to also allow people's eyes to be seen more easily by other people. And also, in astrophysics or astronomy, telescopes often have thin films on them because depending on what an astronomer or an astrophysicist is trying to look at, they probably want the contrast to be better, and sometimes the glare, so to speak, from reflections can sort of drown out what they're trying to actually focus on and study more intently. So those are all ways that, practical ways that thin film interference is actually used. Okay, that's it as far as top content for today. So what I want to talk about now is just really the breakout room goals for today. And they're quite similar to last week. If you're in the Super Tic-Tac-Toe tournament and your next opponent is in as well, then I want you to play your opponent. If you need to collaborate with others on your legacy project, please do so. I've tried to put you in same breakout rooms. If those breakout rooms that I've created don't work for you, then just join each other in a different breakout room. Please remember to submit your progress update report by tonight. And again, if you have any questions or concerns about anything, please reach out to me. I'm happy to help. Just a reminder.